Hello, everyone. So we talked quite a lot about differentiation and integration, but mostly so far we kept them separate. Now we're going to see how they're related using the fundamental theorem of calculus. And very roughly, we're going to see that they're opposites of each other. So this is going to be split into fundamental theorem of calculus part 1 and part 2. Part 1 is going to say what happens if we integrate first and then differentiate. And part 2 is going to say what happens if we do it the other way around, so we differentiate first and then integrate. So let's get started with part 1. So to understand part 1, we need to understand what it means to integrate a function and get another function, right? If we want to integrate and then differentiate, we need to integrate in order to get a function. So how could we do that? Well, one way is with this signed area so far function. So let's suppose that f is any nice continuous function on AB, and we integrate from a up to x. And this gives us a new function called g of x, which is the signed area so far. And what this represents is the signed area from A up to the point X. And if we plug in different X's, we get different signed areas of different regions. So clearly this is a function and it depends on X. So this is the signed area so far. So notice here that the upper limit is a variable, not just a constant. So here, let's see an example. We have a function f where we can easily calculate everything because the graph is composed of straight lines, triangles, and squares, and so on. So let's try to calculate the signed area so far function. G of x is the integral from 0 up to x of f of x. Okay, if we plug in different x's, we should get different values of g. So g is a function. So for instance, if we plug in g of 0, that means we replace x by 0. We have the integral from 0 to 0. Okay, the signed area from 0 to 0 is just 0, right? There is no horizontal part. If we integrate from a number to itself, we just get 0. Okay, if we go from 0 up to 1, that means we do the signed area from 0 to 1, bounded by the graph in the x-axis. So we look at the graph of f from x equals 0 to x equals 1. That the signed area there is just the signed area of this triangle. It's a triangle that's 1 by 1, so we get a half by 1 by 1, we get 0.5. That's the signed area. And we keep going, right? For g of 2, we plug in x equals 2, we get the integral from 0 to 2. So we look at the signed area from 0 to 2, and we can see it's a larger triangle that's 2 by 2. So the signed area is going to be a half times 2 is going to be 2. Okay, and then we keep going. For instance, if we look at if we go from 2 to 3, we get a new area that's a square, which is 1 by 1, and a triangle, which is 1 by 1. So we are going to get an extra area of 1.5. So we go up to g of 3 is 1.5. G of 4, we have to add on an extra triangle that's 1 by 1. So we add on an extra area of 0.5. So we get 4. And then we go to g of 5. Then we're looking at the signed area from 0 to 5. Then we have an extra triangle that's an area of a half, but it's below the axis. So the signed area is going to, we're going to have to subtract 0.5. So we're going to go from 4 to 3.5. And then the same thing from 5 to 6, right? We add on another triangle that has area 1/2, but it's below the axis, so the signed area is minus 1/2. So when we add that on, we're going to go down to 3. Okay. So we see that if f is any function, or at least a continuous function, that where we can actually integrate things easily, g, the signed area of our function, it depends on x. If we plug in different x's, we get different values of g. Okay, so it's a function, we can try to differentiate it. So what is the derivative of g? And it turns out the derivative of g is just f. Okay, so this is the fundamental theorem of calculus part 1. So we have our nice continuous function f. We compute this signed area so far function, g of x. Okay, then its derivative is just little f of x. So if we, roughly speaking, if we start with f and f is continuous, then if we first integrate up to x and then we differentiate, we get back f of x. Okay, so another way of looking at this is with this formula, d over dx of the integral from a to x of f of t dt equals f of x. So what this is saying is that if we want to differentiate an integral where the x is in the upper limit, then all we have to do is take the thing we're integrating and replace the variable of integration by f of x. Okay, and I should maybe emphasize here that why do we switch to f of t dt when we define this function? Well, if the x is already in the upper limit, then we cannot use x also as the variable of integration, right? Each variable should represent only one thing. So when we define this area so far function, if the x is going to be in the upper limit, we have to switch to a different variable here in the thing we're integrating. Okay. So here's a simple example, right? That we're doing the derivative with respect to x of the integral from 0 to x of something. Okay, we're doing a derivative and the x is in the upper limit and there is a constant in the lower limit. All we have to do, as we said, is we take the thing we're integrating and we replace the variable of integration by x, right? So we take our sine e to the t and we replace t by x, we get sine of e to the x. Okay, so if ever you see a question with a derivative of an integral, chances are you're going to want to look at using FTC part 1. So why is this true? So this is a really important theorem, so I think it makes sense to understand why, or at least the idea of why it's true. So let's have this function g of x, which was, as we've been saying, the signed area so far. And we want to differentiate it. And remember, the derivative is g of x plus h minus g of x divided by h and let h go to 0. So we should be interested in these types of quantities. So let's first look at g of x plus h minus g of x. So we have the signed area up to x plus h minus the signed area up to x. That's going to leave us the signed area between the 2 points. So the signed area from x to x plus h. Or here, suppose for the sake of keeping things simple, I choose a positive function, then I can just think about areas. Okay, so we have the signed area from x to x plus h. Here is a graph of our function. And this area under the graph from x to x plus h is well approximated by a rectangle that has height f of x and has width h. Right, so the area from x to x plus h is well approximated by this rectangle that is h by f of x. So that we can use that to approximate our integral, right? The integral represents the area under the curve, and we can calculate the area of the rectangle. It's just the base times the height is just h times f of x. So this is telling us that g of x plus h minus g of x, which is assigned area from x to x plus h, is roughly the area of the rectangle, which is h times f of x. And then if we divide both sides by h, we get g of x plus h minus g of x divided by h is roughly f of x. And now let's let h go to 0. And as h goes to 0, the left-hand side goes to g prime of x by definition of the derivative. And the right-hand side is just f of x. And this roughly becomes an equality as h goes to 0. So that gives us g prime of x equals f of x, which is exactly what we wanted for the fundamental theorem of calculus part 1. And by the way, why does it become an equality as h goes to 0? I mean, if you really want the technicalities, you'd have to study more in-depth calculus, but you can kind of see it also from the picture, right? As the rectangle is getting thinner and thinner, the height of the graph is changing less and less. So if we look in smaller and smaller regions, as we said, smaller rectangles approximate the graph much better. So that's the idea why in the limit we get an equality. Okay, so let's go on and do a couple more examples and see, as we like to push things to have more complicated examples, so let's see how to do that. So first, just a basic example again. So if we want to do the derivative of the integral from 0 to x of this function, of any function, then we just take the thing we're integrating and we replace the variable of integration, here the square root of 1 plus t squared, we replace the t by an x. So we get square root of 1 plus x squared. Okay, so what could be different? So maybe what if the thing we're differentiating with respect to is in the lower limit? So for instance, if we look at the derivative with respect to x of the integral from x to 100, t to the 1000 dt, then we have to swap, if we're going to use FTC part 1, we have to swap things around so the variable of integration is in the upper limit. And remember, we said we can swap the limits as long as we add a minus sign. So instead of integrating from x to 100, we can integrate from 100 to x provided we add this minus sign. And now, if we do that, now we can use FTC part 1, right? We have something that looks like the derivative from a to x of a function. We just take the thing we're integrating and we replace it by x. So instead of t to the 1000, we get x to the 1000, okay? And by the way, you'll have noticed that it doesn't really matter what is in the lower limit as long as it's a constant. It disappears after we do the differentiation. Okay, so next up, what about if instead of having a function of x, like in these examples we had just x in the limit, we had a function of x like e to the x or any function of x, then we have to use the chain rule. So remember the chain rule, there were several ways of saying it, derivative of the outside divided by the inside times the derivative of the inside. Or we can think of it as if we want to differentiate something with respect to x, so if we want to find dy dx, we can make a substitution of u equals some function of x. Then we differentiate with respect to u, and afterwards we multiply it by du dx, and then at the end replace everything by what it was in terms of x. Right, so we make a substitution, do dy du, and multiply by du dx. So let's look at this problem, d over dx of the integral from 1 up to e to the x of ln t dt. Okay, here we don't have an x, we have an e to the x, so it's going to be a general problem. So we make a substitution, u equals e to the x, and that means then we're going to differentiate with respect to u instead, but afterwards multiply by du dx, right? So we're just using our chain rule. And now because we can differentiate with respect to u and the integral up to u, we can apply the fundamental theorem of calculus part 1. We're just going to take the thing we're integrating and replace the variable of integration by u in this case. So we get ln of u. And then we have to multiply it by du dx. Here we're substituting u equals e to the x, so du dx is going to be e to the x. And now at the end, we're supposed to replace u by what it was in terms of x, so we get ln of e to the x times e to the x. But ln e to the x is just x, so this could be x times e to the x. Okay, so yeah, so if the thing that we have in the limits is a function of x, please remember use the chain rule. Okay. Okay, so we talked about what happens if the thing in the upper limit or in the lower limit is a function of x, but what about if they're both functions of x? Then we should use properties of the integrals to write it in a way as a difference of two integrals, where each of them only has x in one in the upper limit. Okay, so here is an example. Suppose we want to differentiate the integral from 5x to 10x of sine of e to the t dt. Okay, so there is an x in both the upper limit and the lower limit. So we should break that up as the integral from 0 to 10x minus the integral from 0 to 5x. Okay, so why is this true? You can either go back to properties of integrals, or if you remember what these represent, right? It's a signed area from 5x to 10x. Okay, we can do that by doing the signed area from 0 to 10x and then subtracting the signed area from 0 to 5x. And if we do that, we're left just with the signed area between 5x and 10x, which is exactly what we started with. And now the advantage of doing this is now we have two things that we know how to differentiate, right? There is just a function of x in the upper limit. And by the way, when you do this rewriting, it doesn't matter what you pick in the lower base here. Here you could have had any constant number instead of 0. It just doesn't matter. It's going to go away when we differentiate. Okay, so if we want to differentiate the left-hand side, we can differentiate the right-hand side instead. So here we have a composition, right? We have to use the chain rule to differentiate with respect to x, the integral from 0 to 10x. So the outside function is the integral from 0 to u of sine of e to the t. The inside function is u equals 10x. We're going to want to do the derivative of the outside function, which is sine of e to the u, evaluated at the inside. So we get sine of e to the 10x. And then we have to multiply by the derivative of the inside, which is 10. And then similarly for the second term, right, it's a composition. The outside function is the integral from 0 to u of sine of e to the t dt. And the inside function is u equals 5x. We do the derivative of the outside, evaluate the inside, which is sine of e to the 5x. And then we multiply by the derivative of the inside, which is 5. Okay, so that about wraps it up for this video. We talked about FTC part 1. That says if we want to differentiate the integral from a to x of f of t dt, we just take the thing we're integrating, f, and we replace the variable of integration by x. So we just get f of x. And if the x is instead in the lower limit, we have to add a minus sign to swap things around. If instead of x we have a function of x, we have to use the chain rule. If there is x both in the lower limit and in the upper limit, then we should subtract them to write it in one of the other forms. Okay, thanks everyone. See you next time.